It's a great pleasure to have Max Alekseyev speak about maximizing the number of integer pairs summing to powers of 2 via graph labeling and solving restricted systems of linear equations. As usual, please mute yourself unless you have something to say. Go ahead, Max.
Thank you, Doran, for the introduction. It's my great pleasure to be here and to present my research. As you can see on the first slide, there is a year of 2024, and that's because I first presented this last year at the IVOCA conference. However, the slides are all updated. It's not the same slides I presented a year ago because I moved a little bit forward with what I did. So anyway, I will explain what was done before and what the new developments. And let me start with the introduction to the problem. We started in 2021, and then Alman and Stan Wagon published problem number 1321. And the problem the problem is about a function which is defined on a finite set of integers. So this function is denoted here by f. And basically, this function considers all possible pairs of the numbers from a given set and checks how many of them sum to a power of 2. Here is a small example in which we have three numbers, -1, 3, and 5. And if we try to sum up different pairs of those numbers, we will get that, in fact, all the pairs give us powers of 2. And so the value of the function is 3 on this small set. And then we may pose a question, okay, let's say we fix the size of the set. What is the maximum number of pairs we can get that sum to power of 2? So the original problem asked for a proof that this function is denoted g of n, by the way, and original problem asked for the proof that g of 10 is at least 14. However, it was quickly improved to the bound of g of 10 is at least 15. Of course, in this case, improvement is done by example. As soon as you exhibit an example with particular number of pairs, you can say that you get a particular lower bound. But then this question inspired a question about how to determine the exact value of g of n for a given value of n. Second. Okay, here we go. And in 2022, in September of that year, Neil presented this problem at very popular YouTube channel called Numberphile, and this brought a lot of people looking at this problem, and there was a lot of developments done. And in particular, it was quickly noticed that computing a value g of n has very natural interpretation in terms of graph theory. Basically, we want to find maximum graph. Maximum here is in terms of the size, the number of edges. So we fix order of the graph, that is number of vertices, let's say n, and we look for a graph with the largest possible number of edges, the maximum graph. So what we want from this graph? We want this graph to have a labeling of its vertices with pairwise distinct integers, such that if we consider any edge and sum up the labels from its endpoints, then we will always get power of 2. And here is an example of such a graph of order 10, whose size is 15, so we have 15 edges. And you can quickly check that indeed for each edge in this graph, the sum of labels at the endpoints of that edge is a power of 2, and that all labels are pairwise distinct. By the way, if anybody has any questions, please raise them right away. It will be much easier for me to answer them. So please feel welcome to interrupt me if you like so. Okay, then in March of 2022, it was proved that, in fact, such a graph cannot contain a 4 cycle with 4 vertices. It's a very easy exercise, so if you like, you can prove it yourself. It's a nice, simple problem. However, for what it means for the problem that we consider, it means that we can restrict our attention to graphs that do not have such a cycle. And such graphs are called square-free graph. That's because we think of the cycle of length 4 as a square, and hence the name. It also severely restricts the number of candidates to consider. So the problem becomes easier for us if we want to consider all possible graphs. And in particular, it led to establishing exact values of function g of n for all values up to 9. And I believe back then it was the sequence which has this ID A352178 was added to the online encyclopedia of integer sequences. And so you can see here what it is. Actually, here we have 11 terms, but it was in fact after the initial 9 terms, a value of the 10th term was independently obtained by Pratt, Bolen, and Meller. And Meller also established that 11th term is 17. So what I would like to present to you today is how to establish a bit of further values. More specifically, I will be talking about n from 12 to 21 inclusively. Now, we already what we have already is the lower bounds. In fact, we have two different lower bounds that restrict sets to certain numbers and allow us to easily compute these bounds. So I mentioned just two of those bounds, maybe there are more, but what is nice is that for the range of our interest, those two bounds give the same value. So I highlighted those values on this slide, and it turns out that these values are the exact values for the function g of n. So we are going to prove that g of n is equal to those values in the range from 12 to 21. Anyway, so to distinguish value of g from the low bound, I denote low bound by letter L. So L of n will be the value of the lower bound for either of these two sequences. Now let us introduce a notion of admissible graph. So a graph, unlabeled graph, is called admissible if we can label its vertices with pairwise distinct integers such that the sum of endpoints of any edge is a power of 2. And I'm going to present to you an algorithm that tests a given graph for admissibility. And furthermore, this algorithm will have a number of applications, such as finding minimal forbidden subgraphs of a given order. And we already have an example of such minimum forbidden subgraph, which is a cycle of length 4. But we will go into look at larger orders, up to 11 specifically. Furthermore, we are going to establish values of g of n in the interval from 12 to 21. As well as we will find maximum admissible graphs of order up to 20. So maximum admissible graph, it means that we fix an order and we want to find an admissible graph which has as large as possible number of edges. So let us start with how we would test for admissibility. And I need to recall a bit of linear algebra. So suppose we have a matrix M, then we have associated notions of right kernel. So what is right kernel? I will think of it as a matrix, which I denote K sub R, such that if we multiply matrix M by this matrix from the right, we will get a zero matrix. And what is, so if we take any vector V, which lies in what we call kernel of M, then it can be represented by a linear combination of columns of matrix K sub R. So that any solution to equation, let me highlight it. Any solution to this equation can be obtained from the matrix K sub R by taking linear combination of its columns. Then we have left kernel. So left kernel is a matrix such that if we multiply our matrix M by this matrix from the left, we will get 0 matrix. And principally, if we have equation V times M is equal to 0, then all solutions to this equation can be obtained by multiplying our matrix K sub L from the left by any vector U. In other words, any solution is a linear combination of rows of matrix K sub L. Then we have Rashchev-Frobenius-Capelli theorem. So in different countries, it may be 1, 2, or 3 names attached to this theorem, but I attached the largest possible number of names. So what this theorem states is that if we are given a vector W and we are solving equation M times V equal W, then solution exists if and only if this product K sub L times W is equal to 0 vector. And last thing that we will need from linear algebra is that if we want to solve this equation, given M, given W, and we want to find all vectors V that satisfy this equation, then it is given by this formula. That is, we take any particular solution, which I denoted V sub 0, and we take a linear combination of columns of right kernel and add those linear combinations to particular solution, we can get any solution to our equation. Okay, with this background in mind, let us now take a look at our problem. So suppose we have a graph G, unlabeled graph G on n vertices and having m edges. Then I claim that it is admissible if and only if the following equation is solvable. The equation is the following: M times L equal X. M here is what is called incidence matrix of graph G. That is a matrix indexed by, so rows of this matrix is indexed by edges of our graph. Columns of this matrix are indexed by vertices of this graph. And so since each edge is incident to 2 endpoints, each row has exactly 2 ones. All other elements are 0 in this matrix. So matrix M is given to us. Since we are given a graph, we are given this matrix. Now, the 2 other entities in this equation, vector L and vector X, unfortunately are unknown. So it's not, if one of them would be known, we could easily solve this linear equation. However, the trouble is that they both are unknown, and furthermore, there are restrictions on what can be L and what can be X. More specifically, L must be composed of pairwise distinct integers. So not just integers, but pairwise distinct integers. And vector X must be formed by powers of 2. Those powers of 2 may be equal, so some of them may coincide, but they must be integer powers of 2. So the question is how to solve this equation, given that we don't know L, we don't know X. The only thing we know is M. So let us start solving this equation for L in terms of X. That is, let us assume that X is composite of element X1, X2, and so on, X sub M. Then we can come up with polynomials, which we will denote P sub I. They are in fact linear polynomials, that is polynomials of degree 1 in those variables, X1 and so on, X sub M, with rational coefficients. Furthermore, by the Rashchev-Frobenius-Capelli theorem, solution exists if and only if K sub L times X is 0. So this is the necessary condition for existence of the solution. And let me denote the elements of this product, k else times x. Please notice that matrix M is known to us, and therefore we know what is its left kernel. So k sub L is also known to us, and therefore we can compute this symbolic product, k sub L times a vector x composite of indeterminates. And I will take all elements of this product and put them in the set which I will denote E. So E is a set composed of linear homogeneous polynomials with integer coefficients representing linear equations in x1 and so on xm. Furthermore, from practical considerations, it would be helpful if k sub L is sparse. So and we can achieve it to a certain extent if we use LLL reduction. I'm not going into details about this reduction. This is just kind of a practical thing. However, it doesn't affect the exposition of algorithm. Now, all solutions L for a fixed x can be obtained by this formula as we discussed before. So by taking linear combinations of columns of the right kernel. And recall that what we want from L, the restriction on elements of L, is that they must be pairwise distinct. So let us first notice that as soon as as soon as the two rows of kr are distinct, we can always come up with a suitable vector u such that the corresponding elements in the vector L are also distinct. So we can enforce, in other words, we can enforce distinctness of elements on those for which we have distinct rows in K sub R. And this is what the following theorem says. So let vector V be integer vector of size K, A be K times S integer matrix with pairwise distinct rows. Then I claim that there exists a linear combination of the columns of A such that if we add this linear combination of columns to our vector V, then we will get a vector with pairwise distinct elements. So please notice that doesn't matter what is V. So V may composite of distinct element, may be composite of all equal elements. Some elements may be equal between themselves. Some others may be equal between themselves. Doesn't matter. We can always come up with the suitable linear combination of the columns of A that will make result of this summation pairwise distinct, containing pairwise distinct element. And in fact, the proof is done by induction on S. The proof is very simple. You can see it fits even with single slide. Even though I'm not going to discuss details, just please trust me that it is all I want to say is on this slide. So there is nothing besides that. Okay, so if we have two distinct rows in our right kernel, then we can have immediately distinct elements in the solution. Therefore, it only leaves us with the question how to enforce a non-equality for the pairs of elements that correspond to the equal rows of KR. And so for each pair of equal rows in KR, let's say we have indices I and J, I will compute the difference between corresponding elements in my solution, that is P sub I minus P sub J, and also I will multiply it by some number just to have coefficients integers. So this resulting polynomial, which I denote Q sub ij, is a integer, is a homogeneous linear polynomial with integer coefficients. So let's consider some cases that may be possible. If Qij is zero polynomial, then it means that we can never have Li not equal Lj. And it means that our problem is not solvable, and it means that G is inadmissible. So if all of a sudden we get Qij 0, it means that we can immediately return answer no, G is not admissible. Another extreme case is then Qij consists of just a single term with non-zero coefficient. If it is just a single term with non-zero coefficients, it immediately means that the corresponding two entries are always distinct. And we can simply ignore such Qij. And the most interesting case is then with Qij contains two or more terms with non-zero coefficients. If this is the case, then we should really take care about with Qij, and at this moment we will simply add it to a set which I will denote n. So the resulting set n consists of polynomials in variables x1, so on, xm, that have to take non-zero values on a solution x to our equation. And I will refer to such polynomials as inequations, because they must not be equal to 0. So I have two sets, E and N, of non-zero linear polynomials in variables x1, so on, xm. And what I want to find, I want to find all tuples of non-negative integers, y1, y2, and so on, y sub m, such that if I evaluate polynomial that comes from set E, I must have 0. And if I evaluate polynomial that comes from set N, I must have non-zero. And just from technical perspective, it is convenient to represent such a family of solutions as a map from set of variables y1, so on, ym into polynomials of these variables. In particular, we have the following convention. If variable is free variable, then it is mapped to itself. Otherwise, it's mapped to a polynomial in the free variables. Here's an example. Suppose I have a map like this. y1 is mapped to y4 plus 1, y2 is mapped into y2, y3 is mapped into y2, y4 plus 3, and y4 is mapped to y4. It means that solution is the following. Oops, sorry. I want to highlight just this part. Solution is the following: 2 to the power of y4 plus 1, 2 to the power of y2, 2 to the power of y2 plus y4 plus 3, and 2 to the power of y4. Okay, I am already, so suppose for a moment that we know how to solve the problem. I will explain it a bit later, but for now let's assume we know how to solve it. Then I'm ready to present you an algorithm that tests admissibility for the graph. So I call it graph solve, which takes as an input graph G, unlabeled graph. And first thing that it does, it's, I believe, up until here, it constructs the two sets, set E and set N, as I explained. This is just the same description, just given a bit formally as presented as an algorithm. And as soon as sets E and N are constructed, this is the part which takes care about solving the corresponding system. Please notice that it calls an algorithm which I call solve in powers, and which gets these two sets E and N. And this is, for the moment, it is a black box. I'm going to explain it later how it is done. But let's assume they already have it, and then just we go over all solutions produced by this function. Then we compute the corresponding values of x in terms of y. Then we solve our equation for L. Now this x is already defined in terms of y's. We solve it not just for L, but we want L to have pairwise distinct elements. And in order to get so, we may need to invoke theorem 1 as needed. Theorem 1, recall that theorem 1 was about how we can get distinct elements relying on distinct rows in right kernel. And after we composite our solution set, we return it. This is so graph solves essentially returns us all solutions to a labeling problem of a graph if graph is admissible, or it returns us empty set if graph is empty set of solutions if graph is inadmissible. In particular, here's a particular case. Then we return an empty set. Recall that if our Q polynomial happens to be 0, then graph is inadmissible, and in this case we immediately return the empty set as a solution. Okay, now I need to explain how to solve in powers. So we are going to solve system of equations and inequations in powers of 2. So let me remind you that we have a system composed of two sets, set E and set N. Both of them are finite sets of non-zero linear polynomials in variables x1 and so on xm. what we want to find? We want to find all tuples on non-negative integers denoted y1, y2, and so on, ym, so that if we evaluate any polynomial from E on such a tuple, we get 0. If we evaluate any polynomial from n on such a tuple, sorry, not on such tuple, but on powers of 2 raised to the corresponding values of y, then we will get non-zero. Okay, and I'm going to present a very simple theorem, which in fact is the foundational for the algorithm solving powers. The theorem states the following. So if we have any finite non-empty subset of non-zero integers and those integers sum to 0, then I can always find two elements in that set that have equal two-adic valuations. So two-adic valuation is simply the highest exponent of 2 that divides this number. So like 2 has valuation 1, 4 has valuation 2, 6 has valuation 1, 8 has valuation 3. So the basically valuation is what is the highest power of 2 that divides a given integer. And the proof is very simple. Let us consider our set and consider element in that set that has the smallest two-adic valuation. Then there are two cases. If no other element has such a valuation, it means that if we sum them up, then valuation of the sum will be equal to this smallest valuation. However, we know that sum is 0 and its valuation is infinity. So this is not possible. And it immediately implies that there must exist another element that has the same smallest two-adic valuation. Okay? Now, how this theorem helps us? Let us consider any equation from our set E. Suppose this equation has form C1 times x plus C2 times x2 plus and so on plus C sub m times xm. Now, there are what we have. It is possible that only one of the coefficients C1 and so on C sub m is non-zero. If only one coefficient is non-zero, then we can immediately claim that our system is not solvable because we will not be able to nullify this particular equation. Recall that x would be power of 2, and if we have just a single x present in the equation with non-zero coefficient, it means that no matter which power of 2 you take, it will always be non-zero. So we cannot nullify this polynomial. And therefore, if this is the case, we can immediately return answer that there are no solutions. Otherwise, if we have 2 or more non-zero coefficients in such equation, then by the theorem that we just proved, some pair of these terms corresponding to non-zero coefficients must have equal two-adic valuations. In other words, we must have equality of this kind. Two-adic valuation of Ci times xi must be equal to adic valuation Cj times xj. And we are going to go over all possibilities here. And we are going to make a substitution. Either substitute xi in terms of xj or xj in terms of xy, depending on the sign of this difference. So I want this coefficient 2 to the power difference of valuations be integer. So one of them will be integer for sure, and we pick that one. So we make this substitution in every element of E and in every element of N. And if it turns out that no element of n is nullified by such a substitution, then we reduce our system to a smaller system with smaller number of variables. So if we originally had m variables, then after substitution we will have m minus 1 variables, and therefore we can proceed solving the system recursively. And furthermore, we will also add this polynomial to n. Why we add it to n? It's to disable this equality in future. So we are going to explore this equality at this particular moment, but in future we don't want to have it. And therefore, by adding this difference to n, we disable it in future. opposite way around. So I'm going to present a pseudocode for solving powers. So solving powers gets to sets E and N. If it turns out that E is empty, well, then we simply return the identity map, because every variable is free, nothing to satisfy. Otherwise, if it's not empty, we pick any equation, C1 times x1 and so on, Cm times xm from E. We look at non-zero coefficient in such equation. If it turns out that there is a single, if there is just a single coefficient that is non-zero, it's immediately return empty. There are no solutions. Otherwise, we are going over all pairs of indices from those that have non-zero coefficients, and we basically do this substitution that I explained, get the smallest set E prime and N prime, and we recursively call the same function, solving powers, and just from solutions update solution to a bigger system. Now let's discuss applications of those two algorithms. So let's start with the minimum forbidden subgraphs. So minimum forbidden subgraphs of small, we're going to find them of small order up to 11. And it is easy to see that minimum forbidden subgraph must be connected. And C4 is an example of MFS of order 4. So we're going to, and there are no graphs of smaller order that is forbidden. So we are going to look at the larger orders. We are using Sage Math software, and in particular, it provides access to Naughty tools for generating graphs, and Naughty can provide us build graphs both connected and square free, so very convenient to use for generating candidate graphs. So algorithm for finding MFS is quite simple. We simply let set S be empty set in the beginning. This form loop over orders from 5 to whatever bound we chose. 11, I did it for up to 11. Then we generate each connected we generate all connected square free graphs of order n. We check if it contains any graph H from S as a subgraph. There is a function in Sage Math which can check if one graph is subgraph of another. If it turns out that it contains some subgraph, then it's definitely not minimal, and therefore we ignore it, go to the next candidate. Otherwise, it turns out that it doesn't contain any subgraph from S. We call our graph solve algorithm that I just explained. If it turns out that it returns us no solution, it means that we have an MFS and we add it to the set S. So very straightforward. Here's an example of next to MFS after C4. So there are no other MFS of order 4 besides C4. There are no MFS of order 6, and the next order for which we have MFS is 7. And for order 7, these two guys are forbidden, minimal forbidden subgraphs. Then there are no MFS of order 8 or 9. There are 15 MFS of order 10. Then there are 77 MFS of order 11. And I chose MFS of order up until 10, used for quick filtering. So before we invoke graph solve algorithm, whenever we want to test admissibility, we first test if any of the minimum forbidden subgraphs is present in a given graph as a subgraph. If any of the minimum forbidden subgraph is present as a subgraph, it immediately means that our graph is inadmissible, and we don't need to even call graph solve algorithm. Now, let us consider the problem of establishing values of G sub n. So values up until 11 was established before. Here are the values. And for n from 12 to 21, we have lower bound, 19, 21, 24, and so on. And I'm going to actually show that for each n in the range from 12 to 21, we have G of n equal to the lower bound. So how are we going to show it? Essentially, we're going to establish that we cannot have more than L of n. In other words, we are going to show that every graph of order n and size L of n plus 1 is inadmissible. And in order to do so, we need the following theorem. The theorem has three statements. First statement is that if you have admissible graph of order n and size e, then its minimum degree must be at least e minus g of n minus 1. And the proof is the following. It's actually two lines. So if G is an admissible graph of order n and e edges, let us consider and suppose it has a vertex of degree smaller than e minus g of n minus 1. Let us remove this vertex from the graph. The resulting graph will be also admissible. And on the other hand, it will have size greater than g of n minus 1. But this contradicts the definition of G, because G is the largest size of admissible graph. So this simple two-line proof shows us this first statement. Now, next statement. Next statement is that g of n can be bounded in terms of g of n minus 1. Namely, we take g of n minus 1 multiplied by n over n minus 2 and take the flow function, rounded down. And the proof is also very simple. So here is down below, you can see the proof. So suppose that minimum degree is at least e minus g n minus 1 as proved in the first statement. Then the size of g is at least n times this minimum degree over 2. And from this we conclude that that is e is at least this number. Or if we solve it for e, please notice that in this inequality we have e present in the left hand side and the right hand side, but we can solve it for e, and if we solve it for e, we will get exactly this bound. And furthermore, it remains to notice that how g of n is defined, the admissible graph of order n and size g of n exists, and therefore we can take equal to g of n and get this bound. Finally, statement number 3. Statement number 3 is a bit more involved, but it's also I can also fit the proof into a single slide, which is shown here. So let me skip it. It's not hard as shown here, but I believe I'm running a little bit of time, so let me go into more interesting stuff. So we are going to use this theorem iteratively for n from 12 to 21, and in fact each time we will get that the condition of the first statement holds, and therefore admissible graphs must be connected. So I really need to simplify our life. I really need to have them connected, and therefore I can focus on connected square-free graphs, which I refer as candidate graphs. So now let us establish a value of g of n for n from 12 to 16, I believe, on this slide. So basically what we do here, we notice what is the minimum degree. For n equal 12, the minimum degree must be at least 3, according to our theorem. And if size of it is L of 12 plus 1, which is 20, then we have just 18 candidate graphs, and we solve them, we test them for admissibility and verify that no such graph is admissible, meaning that g of 12 must be 19. Similarly, for n equal 13, we generate all candidate graph of order 13, size 22, and minimum degree at least 3. There are 173 such candidate graphs. We test them all for admissibility. No graph is admissible, and therefore we conclude that g of 13 is 21. Then from this value of g of 13, we immediately get an upper bound for g14 as 24, which matches the lower bound. So we get value of g of 14 for free. No computations needed in this case. Just theorem gives us the upper bound, which matches the lower bound, and so we get exact value. Then for n equal 15, we again need to make a bit of computations. Namely, we have 8,280 candidate graphs that we need to test for admissibility, and we do so. No such graph is admissible, and we conclude that g of 15 is 26. And finally, for n equals 16, again we get our value for free. No computation is needed. Then let us take a look at n equals 17 and n equals 18. For 17, we get that we need to look at size 32 and minimum degree at least 3. In fact, the minimum degree should be exactly 3, since otherwise such graph is not possible. But unfortunately, if we take the route we considered it for the previous graphs, there are over 1 million candidate graphs to consider. In principle, can be done, maybe employing some high performance computing, but I decided not to consider this many graphs. Instead, I took an alternative route. Namely, we noticed that the removal of vertex of degree 3 from our admissible graph of order 17 and size 32 would result in what we call maximum admissible graph of order 16. And therefore, if we have all maximum admissible graph of order 16, then we can simply try to add back this vertex of degree 3 in all possible ways and verify whether we can get an admissible graph this way. So we constructed all those max of order 16, added vertex of degree 3 in all possible ways, verified that no admissible graph can be obtained this way, and so G of 17 is 31. Value for 18 we get for free again, because the upper bound matches the lower bound. Now, for 19, approach is somewhat similar to 17. Again, we considered max of order 18 and showed that you cannot add a vertex of degree 3 to get admissible graph of order 19. And so G of 19 is 36. And for order 20, we noticed that this is the first time then minimum degree is bounded by 4. And therefore, the number of candidates graph is relatively small, thanks to this bound for the minimum degree. So there are just 15,156 candidate graphs, so we can go over them all and test for admissibility, and turns out no one is admissible, so G of 20 is 39. Now, for 21, so a year ago, I got values up to 20, and then I made further advances to value of G of 21. So for n equal 21, our theorem implies that the graph that we need to test has size 42, and minimum degree should be at least 3, but also we can easily get that it may not be greater than 4. So minimum degree is either 3 or 4. If minimum degree is 3, we follow the previous route by constructing maps of order 20 and trying to add vertex of degree 3 in all possible ways to it. If G is equal to 4, then nice thing is that G must be 4 regular in this case. And furthermore, since G is square free, then it GERS, that means the length of the smallest cycle in this graph is either 3 or at least 5. So if it is 3, then we do the following thing. We remove the 3 cycle from our graph, and furthermore, we remove 2 degree 2 vertices in the resulting graph, and we obtain max of order 16, and then we consider all max of order 16 and try to reverse these 2 operations back and check if the graph we obtain is admissible. It turns out that no graph is admissible. And if GERS is at least 5, then in fact there exist just 8 such graphs. They were already constructed by a tool called GenReg, and those graphs can be obtained from this website. So for me, it was just to take those graphs and test them for admissibility. It turns out again that no such graph is admissible. So we conclude that G of 21 is equal to 41. And this concludes the proof. However, this concludes the proof only modulo the max. So I highlighted in blue all statements in which I used max of certain order. So in order to really complete the proof, I need to have those max handy. So let's discuss how we construct max. So max of order 14 can be obtained directly from candidate graphs generated by Naughty. And in this case, we have 2,184 graphs, square free connected graphs of minimum degree 3. Among them, we have just 4 max. These are the 4 max, and furthermore, this 4 max is even labeled. Then for order from from 15 to 18, we consider max can be obtained in 2 different ways. Either they can be extended from a smaller max, or we can be de novo Mac, in which case the minimum degree is so if minimum degree is exactly the difference between these two values, then it must be extended from a Mac of smaller order. However, if minimum degree is at least one more than this difference, then these graphs, what we call such graphs, de novo candidate graphs, and we generate them explicit by Naughty tool again. And for n equal 15, it turns out that there are 20 extended and 8 de novo max, so total is 28 max. For n equals 16, there are just 2 max. For n equals 17, there are 11 extended and 7 de novo max. And for 18, there are just 2 max. However, we need also max of order 19 and 20. For order 19, it's very easy to get max of minimum degree 2. There are just 15 of them. However, number of de novo candidates graph appears to be prohibitively large. I don't even know how many of them. Naughty tool cannot even compute the number of those graphs. Therefore, the approach that I explained on the previous slide doesn't work here. Instead, I took a different route. A different route in this case is making a step down from max to what I call submax. Submax are graphs of size 1 less than the maximum possible. And so, and therefore, in order to get max of order 19, I constructed submax of all orders up to 18. So here is explanation how it is done. So a bit of computational work here, but eventually I was able to get 7 what I would call de novo max, and therefore total number of max of order 19 is 22. And max of order 20 is very easy because of the large minimum degree, and so they can be obtained from as an extension of max of order 19, and there are just 2 such max. So all max are constructed, and therefore my proof of the theorem now complete. And just to show how efficient I was, like it's very hard to give precise complexity estimate for the algorithms. However, practical experiments show that they are at least in the range in which I applied those algorithms, they are very much practical. You can see some running time shown on this slide, how much time it takes for the graphs to be tested. Just some concluding remarks that solving powers can be easily extended to powers of other primes and maybe even to arbitrary integers. However, for arbitrary integers, maybe a bit more involved than just 2 powers, because there was nothing special about power of 2. I could similarly consider power of 3, and my foundational theorem, simple foundational theorem about valuations, I could similarly consider valuations base 2, not base 2. Then we applied solving powers to linear equations, and maybe it's possible to extend it to polynomial equations of large degree. So also I don't see immediate obstacles for extension in that direction. Performance of solving powers is sensitive to number of non-zero coefficients. That's why, from practical perspective, it may be helpful if we can come up with a sparse left kernel. So please notice that left kernel matrix is formed by some basis of the left kernel, and basis is not something unique. We can come up with different bases. And among those, we may look for bases that are sparse. So if we're able to come up with a sparse basis, we may improve performance of our algorithm. I tried also to perform reduction on every step. We create a new set of E in the recursive calls. However, it looked like it doesn't provide much benefit, but maybe I did it wrong. So I really would like to explore more in that direction, because it seems like it should help, but somehow I was not able to get it right away. And the last remark is that preprint of the paper is available on arXiv, and soon the full paper, including the case of n equal 21, will appear in the Journal of Computer and System Sciences. And so I believe this is my last slide, and thank you for attention.
Thank you very much for very, very complex, but using beautiful, simple ideas. There's time for questions, but I have a quick question. In the original article by Delahaye, there were these beautiful graphs with 9 vertices that you came up with. So that was by trial and error, or you already use this very systematic approach?
Graph with how many vertices?
9 with 3 triangles meeting on
9. So I believe, okay, I believe
nine
you're talking about. So I believe one of those graphs was already discovered before. However, it was checked manually, so there was some number of lines in the proof that kind of checking various cases in order to prove that it's not admissible. For me, it's just running my algorithm, and my algorithm tells me that it's not.
So C4 was the first one, right? And then there was the next one in these two.
Next one after those two guys.
Yeah.
Okay, so actually I may let me quickly show you. So I want to change share into my screen. Just a moment. Okay, maybe this one. So first of all, I can show you a small code that generates just candidates of order 12, 20, 30, order 12 size 20, order 13 size 22, order 15 size 27. You can see that in Sage, it's just like 3 lines to get result. Result is highlighted here. For n, we have this many candidates. And then I have my code posted on GitHub. So this is a GitHub in which we have Sage math codes as well as graph data. So this graph data contains all these max, submax, and other kinds of related graphs. So you asked what are other after. So you can see that this is the C4. These are the 2 guys I showed on the slide. And these are the follow of order 10. So I can quickly show them to you. Let me... So I will put this list in here.
They're live, yeah.
And for, let's say, G6 and L, graph G6 dot show. And I believe this is it. So let me run it. And here are those graphs.
Yeah, wow, it's amazing. That's a great experimental math. Wow, great.
Even though, so please ignore labeling. Labeling is irrelevant here, but the these graphs are in fact unlabeled.
Yeah, beautiful. Are there other questions to Max?
Yes. Max, do you have any sort of effective bound on the largest power of 2 given n that you would expect if the graph is admissible?
Oh, wow. Oh, I didn't think about this. It's a nice question, but I didn't think about it. Maybe it's looking kind of at details how algorithm works. Maybe it's possible to come up with such a bound, but I don't have immediate answer.
Yeah.
So I may take a look later. Thank you for your question.
Or don't you just multiply every vertex by 2 and you scale it up to arbitrary power of 2?
That's true, and that's why I have 3 variables in the solution. So if you recall, I have some of the variables are free, and that's exactly takes care of what you just explained.
Right. But what I was saying, in other words, if a graph is admissible, can you restrict your search to powers below a certain number? That's I guess the question I had.
Oh, okay.
Yeah, at least canceling common factor. So maybe taking as small as possible powers, and maybe we can bound them. Yes. I don't have an immediate answer, unfortunately.
More questions to Max? Well, thanks so much for a great talk. All right, please end this and see you next week.
Okay,
and
thank you.
Please send me the slides. Thank you very much.
Okay, thank you. My pleasure. Thank you.
Thank you.